Okay, I would like to thank the organizers. It's a pleasure and an honor for me to speak at this momentous occasion. So I want to speak about representations of periodic groups. That will be most of my talk, and towards the end we'll see how this connects with the theory of endoscopy and Leibniz correspondence, and possibly questions that go beyond endoscopy. But for now, let me just start with a motivation. Let's recall, if we have a connected reductive group over the real numbers, Harishchandra's classification of irreducible discrete series representations. So the theory says G has discrete series irreducible representations if and only if there is an elliptic maximal torus. And if such an elliptic maximal torus exists, it is unique up to conjugation by the R points of G. And then the irreducible discrete series representations are in one-to-one correspondence with the following data. We're taking a B and a theta, where B is a Borel subgroup of G containing the elliptic maximal torus S, and it is defined over C. And theta is a character of the R points of S, whose differential is dominant for B. And we can slightly restrict our attention to those thetas for which this differential is also regular. And if the differential is regular, it's going to determine B. So B becomes redundant. And then we can rephrase this in the following way, saying that the regular irreducible discrete series representations, and I think this notion of regular I just made up for the talk. So these are those coming from characters theta whose differential is regular. They're going to correspond. I forgot to say here, these are to be taken up to conjugation by the R points of the Weil group here. So we can rephrase this by saying the following. We're looking at pairs, S, an elliptic maximal torus, theta, a character of it whose differential is regular, and now up to conjugation by the R points of G. And this is equivalent to that because S is unique up to GR conjugation. So that's as far as real discrete series representations are concerned. Now let's think of...
Could I remark that topic is a topic that every number theorist who writes about Shimura varieties should be obliged to read before his articles are published. There's a remarkable ignorance, I think, of number theorists on the basis of the theory of Shimura varieties. Do you agree? Thank you, Richard.
So let's now take F, a finite extension of QP. Maybe we could even allow it to be a function field. But let's assume that P does not divide N. And what is N? We're considering G to be GLN. And then we're asking, well, can we parameterize the irreducible supercuspidal representations? And this was done by work of Howe and Moy. So Howe and Moy say the following. Irreducible supercuspidal representations of G of F are in one-to-one correspondence with the following. These are degree n field extensions of F together with the character on the of E cross, which is admissible. I don't want to recall, the admissible is a notion invented by Roger Howe. It's a collection of two technical properties that I don't want to recall. But I want to draw attention to the fact that this is very much analogous. Degree n extension of F is the same as a maximal torus of GLN up to conjugacy. So we can really write this as, just as above, pairs of a maximal torus of G and the character of its F points, which has a certain condition, admissibility, all taken up to conjugation by G of F. So then now, but it's slightly different. See, Here we were talking about regular, so we didn't quite capture all discrete series representations. Here we're talking about supercuspidal, so not literally discrete series. We're omitting a non-supercuspidal discrete series. And now we're characters with a certain admissibility condition, but nonetheless the pictures seem fairly similar. So a natural question to ask is then, what about general G? Can we have a simple, in these terms, parametrization of supercuspidal representations of a general reductive group G? So first, let us restrict to G that split over a tame extension. This will have something to do with this assumption here. P does not divide N. It's not the same, but G is already split. But there are certain conditions on P. And then in that situation, there is a general construction due to Ju Kang Yu of supercuspidal representations of G. And it takes quite a complicated looking data in order to produce a supercuspidal representation. The data looks like this. You need to give yourself a tower of connected reductive subgroups of G. And each of these GIs, so this is connected reductive subgroup of G, and it becomes a levy over a tame extension. It's not a levy over G. In fact, it is forbidden to be a levy over F, but it becomes a levy over a finite extension. So if these are called twisted levies, if you haven't thought about them, the most basic example is any maximal torus is a twisted levy because it splits over some finite extension and then it becomes a minimal levy. And then you're given also a sequence of characters. So these are linear characters of these levy subgroups. Such a character has a notion of depth. How deep do you have to go in a certain filtration before the character becomes trivial? And the depths are supposed to increase. And then finally, a depth 0 supercuspidal representation of the smallest of these groups. So that's the data, as you see, quite a mouthful, that the construction of JKU takes in order to produce an irreducible supercuspidal representation of G. So from here we get irreducible supercuspidal representation of G of F. So this is Ju Kang Yu's construction. Maybe I should put it here. And so it came out 2001, and it has since been studied by different people. So here are a few important results in that direction. In 2007, I believe, Julie Kim proves that this is in fact surjective if the residual characteristic is not too small. In fact, one can write down, if one wanted an explicit bound, so it's not an existential bound, there are certain conditions you can explicitly quantify. And if P is not too small for G, this is an exhaustive construction of all supercuspidal representations. And then the second result in this direction, 2008, due to Hakim and Murnahan, they describe, in some sense, the fibers of this map. So what they do is they introduce an equivalence relation on data of this kind and prove that the equivalence classes of this equivalence relation are precisely the fibers. So now the question becomes, can you simplify using this equivalence relation?
This is known not to be surjective when P is small.
This is known not to be surjective when P is small. Yes, already in the case of GLN, when you have P dividing N, you do see representations that do not come from this construction.
And the understanding of the missing ones
is quite limited at the moment, as far as I know. So there is, for example, a construction 2014 or 15 due to Yu and Reader of so-called epipelagic representations, which has the virtue of working for any p, but it constructs a very, very narrow section, very narrow slip of representation, so-called positive depth, so ramified, but in a minimal way. And it works uniformly, but that gives you just a small glimpse of what is out there. So in general, there are constructions of Schoen-Stevens for classical groups, symplectic orthogonal, which are exhaustive for all p not equal to 2. And there is the construction of Bushnell and Kutzko from a while back for GLN. But as far as a general group is concerned, exceptional groups and so forth, very little is known.
And even for GL2, the extraordinary representations are not of this type, are they?
No. So exactly. So even for GLN, where this construction specifies to a how construction, when p divides n, the construction would still work. It just wouldn't be exhaustive. But for GLN, the representations are understood even for small p by the work of Bushnell and Kutzko. It's just quite a bit more complicated.
On the Galois side, are you essentially restricting to things that are on wild inertia or somewhat characters?
That's exactly right. So this would correspond to the Bushnell-NER notion of essentially tame, which is what you're saying. Yeah. So I'll get to the Galois side towards the end, and you'll see exactly what the parameters are. Okay, so so the question becomes, well, can you somehow, simplify this in such terms? And so I'll just write this down simply as simplification. And simplification in those terms. So I would like to have a description like this. And first of all, there is an obvious obstruction to doing this, and the obstruction comes from unipotent representations of reductive groups over finite fields. So there do exist cuspidal irreducible representations of finite groups of Lie type which do not admit a description of these simple terms. They're not limited to only unipotent representations, but the existence of the unipotent representations is kind of, that's the archetype of such. So, well, what are we going to do? Well, in the real case, we're willing to restrict our study slightly to the so-called regular. So why don't we just see how far we can get if we simply avoid this complication? So the restriction here is, oh, and by the way, depth zero supercuspidal representations by the work of Prasad and Moy are very closely related to cuspidal representations over a finite field. So if you have a difficulty over the finite field, it will be reflected immediately on the depth zero level. But it turns out we make the following restriction. We look at such data where the depth zero SOCO, the thing you start with, is a regular Deligne-Lustig representation. Which means you're looking at a character in general position of a maximal torus of your finite group of Lie type, and you construct the Deligne-Lustig character. It's automatically irreducible. It's a virtual character, so after a plus-minus sign, it's actually an irreducible character. And that's what I mean by a regular Deligne-Lustig representation. And then there is a procedure which allows you to obtain from that a representation of the p-adic group G0. So I won't go into the details, but this is the restriction I make. So let's consider all such data where we put this restriction on pi minus 1. What can we say then? Well, let me give you a definition that is going to tell us, tell us what this is in our setting. So a tame regular elliptic pair, S and theta, consists of the following things. First of all, S in G is a tame elliptic maximal torus. So just to remind people, the word elliptic simply means when you divide S by the center of G, it's an anisotropic torus. And tame means that its splitting field is tamely ramified over the ground field. And then we have the following condition. Let's look at a subsystem of our root system. So the maximal torus, of course, leads to a root system, all the roots of S in G. And we're going to be looking at, I didn't say what, sorry. Here, theta is a character. So theta is a character of the F points of S. And I'm going to now look at the subsystem of the root system with the following property, that if I let me write it down and I comment what it is. So I take a root, I look at the corresponding coroot. The corresponding coroot will be a map from GM into S. That morphism will be defined over some splitting field of S. So I take E to be such a splitting field. Then it would give me a map from E cross to the E points of S. I'm going to restrict this map to the topologically unipotent elements. In other words, 1 plus the maximal ideal. And then I'll take the norm. And then I can take the character. And I want this composition to be trivial. So that would give me a subroot system. And I want on this subroot system that the action of inertia preserves a set of positive roots. This may seem a little cryptic. We can reformulate it in terms that are more easily understood as follows. Let's take G sub 0 to be the reductive subgroup of G with this root system. Then all this is, and it by construction contains this torus S. This is equivalent to saying that this torus S, when you base change to the maximum ramified extension, becomes a minimal levy. That's equivalent to saying this. And the final condition is that there is a certain regularity condition on the character, namely the stabilizer of this character, when you restrict it to the Ivahori subgroup of the torus, in this smaller group G0 is, in the normalizer of S, of course, of G0, modulo S of F, this is trivial. So the stabilizer of this character in the rational Weyl group of this torus S in the small group G0 is trivial. So that's the somewhat usual regularity condition on characters, that no Weyl element fixes the character, but I'm only taking Weyl elements in this smaller group. So these are the conditions. They're explicit conditions, which you can check, or you can program into a computer to check for you if you want. And the theorem now is the following. Use construction gives a bijection between such the set of regular elliptic tame pairs up to GF conjugation and regular supercuspidal representations. So the regular supercuspidal representations were those that arise from use construction from data where pi minus 1 is regular Deligne-Lustig character. And the theorem is that they are parametrized pretty much exactly like discrete series for real groups are parameterized, or supercuspidal representations for GLN are parameterized.
So just to be clear, the regular supercuspidal representations correspond to these, and these are the ones for which, first of all, you have the condition on P and N, say for GLN, P does not divide N.
Right.
And together with this second condition that they don't have, that they have a regular Deligne, come from a regular Deligne-Lustig representation.
Right.
Is that
So you can think of them is that the only condition is being this. But if P is not large enough, this construction is not going to be surjective. So these are somewhat different statements. But the regular ones are the ones that arise via this construction for pi minus 1 being a regular Deligne-Lustig representation. But you're right, so let me say what the assumptions on P are in order for this theorem to be true. So I assume that P is not bad for G in the sense of Springer and Steinberg. So I'll remind you that there is a list of bad primes. So it's 2 for, well, I think B and C, and D, 2 and 3 for E6, E7, F4, G2, and 2, 3, and 5 for E8. If memory serves, these are the bad primes, so these you should avoid. And then there is another condition which can be avoided under some additional work, but the theory is cleanest if you say that P does not divide the order of the fundamental group of G derived, which in all cases except type A is automatic from the first condition, and only in type A it's an additional condition that is implied by P not dividing n when you have type A n plus 1. But you can remove this condition with some additional mumbo jumbo. But
so using Crisco and Bushnell, for example.
Removing the condition?
That's right, and because that's really hard, right, to get.
No, removing this condition is just a matter of using Z extensions. So it's not.
But you're still in those cases you're still excluding a good number of supercuspidal representations because of your.
Exactly. Well, in all cases where Kim's result is not true, where this is not surjective, you're excluding a good number of things. When P is large enough for this result to be true, so in particular all of this is also assumed, where this map is surjective, then you're still excluding something because you're still assuming that pi minus 1 is regular, but you're excluding very little. For example, in SL2, you have 4 supercuspidal representations which are not regular, and all the others are. So that gives you a rough idea that this regularity, it's a non-trivial condition, but you're excluding a small number of things. Whereas if P is small for G, so that this is not surjective, you're excluding much more.
I think you said this, but I didn't get it. I guess I could ask Julie. What's the statement of the theorem? How big must P be?
To be honest, I don't remember off the top of my head. Julie can certainly say more.
Exponential, or in terms of all the data of G, or is it?
In terms of all the data of G, we would want things like the exponential map converges on the largest possible domain it could, and it's things like that. So I think, is it the same conditions that the Bach and Reader put in their paper? It's similar. It's even stronger than that. Okay, so a similar condition that I know of is something like P is larger than twice times the ramification degree of F over Q plus the dimension of the smallest faithful representation of G, or something of this sort. But Julie says it's even maybe a little stronger than this. Yeah, but it's an effective, it's not one of these logic things where it's an effective, right. Okay, so this is as far as, I don't want to go into the details of, but I want to say one actually thing, which is this definition, even though it looks so weird, in the case of GLN, it specializes precisely to Howe's notion of admissibility. So this generalizes Howe admissibility to other groups. I don't want to go into the proof of this. I'm happy to discuss this privately afterwards, just in the interest of time, because I want to move on to the study of characters of these representations. So let's go into character formula, which is where something very interesting is happening. So let's take a general a representation that comes from this construction, not necessarily regular for the moment. Then there is work of Adler, Spice, and de Backer, which gives a formula for the values of the character, Harishchandra character of such a representation. And this formula has the following general shape. So this is the Harishchandra character. You have to take your regular semi-simple element you put in, and you have to split it as a product of so-called head and tail. I don't want to be explicit about this. But you can, if you're familiar with the topological Jordan decomposition, it's a certain generalization of that. And then there is a sum over, you're conjugating over a certain set. I'll be more precise when I specialize to the setting where I need it. For now, I just want to give you a general flavor. And then in here, you have certain roots of unity that depend only on the head. There are 3 of them. All of them depend on the head. And of course, this may look very vague, but the point of my discussion will be to describe exactly what they are. But for now, let me just put them like this. Then you have the character. OK, let me explain what this is. You can take this U datum, and you can truncate it by removing the last group here and the last character here. And then it becomes a U datum for the next smaller group. And that U datum will give you a representation of that next smaller group. And that is this representation. So it is, in some sense, a recursive formula that gives the character in terms of smaller groups, and so forth. So, and this is all in terms of the head. And then the tail enters via the Fourier transform of an orbital integral on the Lie algebra of the centralizer of the head. So this is what this is the qualitative structure of this formula. And this formula at the moment only works if this penultimate group is compact mod center. OK. Now, let's specialize to regular supercuspidal representations, the one that we're studying. So now pi will be pi of s and theta. And let's specialize to gammas, which are actually points of s and which are shallow. What does shallow mean? Well, shallow means that in this decomposition, there is no tail, there is only a head. And maybe an even stronger condition. I don't want to be too specific about it. But under these assumptions, what you can show, first of all, is that this compactness assumption is unnecessary. So you can actually apply this formula in the generality of the representation you have. And secondly, you can go ahead and try and undo the recursion formula here. Since the element is shallow, there is no tail term here. And after you undo the recursion formula, what you end up with is the following formula that looks all of a sudden much nicer. You're summing over elements in the Weil group. And then you have again these roots of unity. Where now I'm collecting the corresponding root of unity from each iteration of undoing the recursion, and I'm putting them all together. So I'm putting all these ES sub SR together from each step and so forth. And then at the end, you have the character, this character here, that parameterizes the representation, evaluated it here. So this is what it looks like. And now, this may look familiar to you. This doesn't look too far from being the Weil character formula. All right, so, but the question is, what are these strange roots of unity here? What can we say about them? Now, the first thing we can say is that this root of unity here is a character of S of F, and so we can subsume it together with this character. In other words, one thing we can do is we can shift our parameterization by this character. Another thing you can do is you can look carefully into the JQ construction and realize that there are certain choices being made there, and if you make a choice differently, this character actually disappears. So it's somewhat of an artifact of the construction, and this is reflected in the property that this is a character of a torus. Where these here are not characters, these here are quite subtle, and they depend on the fine structure of the p-adic group, which more specifically on the following set. Namely, the set is called or at x alpha, and it is, let me say how it is defined. You look at all real numbers where something happens. Now, x is a point in the building, the Bruhatidze building of G. And Moy and Prasatev defined a filtration by lattices of the Lie algebra of G for every point in the Bruhatidze building. And what we're interested in here is at what points does this filtration change? Where do this filtration is indexed by real numbers, but the places where it changes are discrete, and you're capturing where are these changes. So this is what I'll write down here. It's not too important to understand precisely what this is. I just want to give you the flavor of what kind of objects these are. So these are signs that depend on the structure of the filtrations of the p-adic group given by Bruhatidze theory. All right, and so one thing we would like to do is we would like to express these roots of unity in a way that hopefully has as little to do with structure of p-adic groups as possible, and as much to do with just basic Lie theory, hopefully in a way that's interpretable in terms of the dual group. And for this, one thing that you need to do is you need to understand this set in terms of Lie theory. So let me introduce some notation from a paper of Langens and Schallstadt on transfer factors. This is basic notation about roots. So let's look at the root system of S valued in G. Because S is a torus defined over F, this root system receives a Galois action. So we can look at how does the Galois group act on this root system. And we say that alpha is symmetric if the Galois orbit of alpha contains the negative of alpha, and otherwise the root is asymmetric. And then we can look at the stabilizer of alpha under the Galois group. And you can look at the stabilizer of the set plus minus alpha under the Galois group. So this will be potentially a slightly larger group, larger precisely when the root is asymmetric, and then it will be of index 2. And then we define F alpha to be the field of definition of the root alpha, so the fixed field of gamma alpha, and F plus minus alpha to be the fixed field of gamma plus minus alpha. And this is a field extension of degree 2 when the root is symmetric, and these are the same when the root is asymmetric. Okay, and it turns out that there is a very simple sign invariant that can be defined for any connected reductive group over a local field, p-adic or not p-adic. The sign invariant assigns to every symmetric root a +1 or a -1. And it's defined in the following very simple terms. You take, so F alpha, what do you do? Well, you fix an x alpha, a non-zero vector, in the one-dimensional root space in the Lie algebra corresponding to alpha. Since the root is defined over F alpha, this one-dimensional line is defined over F alpha, and you can fix an F alpha point of it, which is non-zero. And let tau be the non-trivial element in this Galois group of order 2 of F alpha over F plus minus alpha. In other words, the Galois element which sends alpha to minus alpha. If you apply this Galois element to this root vector, you get a root vector in minus alpha. When you bracket them together, you get a multiple of the core root. You divide the one by the other, you get a scalar. This scalar is immediately in the field F alpha, but you can check very quickly that it's actually in the smaller field F plus minus alpha. So it's just waiting for you to evaluate the local class field theory character on it. So here kappa alpha goes from F plus minus alpha modulo norms F alpha to plus minus 1. And you can check that the choice of x alpha doesn't matter. So this is something canonically defined, and it gives you a +1 or a -1. And this is something that is very well known from the theory of real groups, where symmetric roots are called imaginary, and imaginary roots can be compact or non-compact. And this is exactly +1 when it's non-compact, -1 when it's compact. So this generalizes this distinction of roots to periodic groups as well. And it turns out that this simple Lie theoretic invariant can tell you what this set is that is defined in terms of Brouhat-Hitz theory. So the proposition is the following. This set of Brouhat-Hitz theory is going to be Z properly rescaled if alpha is ramified. Oh, I forgot to say, you say that alpha is ramified or unramified depending on this field extension being ramified or unramified. So either if Z is alpha is ramified or alpha is unramified, and this sign invariant is +1, and it's Z shifted by a half if alpha is unramified, but the sign invariant is -1. So it's kind of surprising that even though the definition is in terms of Brouhat-Hitz theory and filtrations, the actual result ends up being independent of all of this structure, and it's just a Lie theoretic statement. And so with this, we can actually evaluate all of these roots of unity in the character formula and write down a coherent character formula. And it looks like this. So how much time do I have? Be with
Sleep.
Be with asleep. So what do we say?
Can I ask you a question?
Oh, go ahead.
I mean, when I ask myself, is why you're not classifying stable characters first and then the endoscopic structure? One would think that would be easier.
I mean, you'd see that the character just falls out already. I mean, but I mean, let's talk about this afterwards. So here's the character formula. Okay, let me just write it down because nobody's telling me how much time I have, so I'll just
10 minutes.
10 minutes. Okay, so who's
12 minutes.
12 minutes, good. All right, so I'll write down the character formula. Here it is. Again, for elements, is it still? Yeah, elements in S of F, shallow. It looks like this. There is something well known in the theory called the Cotwitz sign of your group. It's +1 or -1. Then you have a root number, epsilon at a half, of the following virtual Galois representation. Let me write it down and explain it afterwards. So we have our torus S. We take its character module, complexify. That's a Galois representation. On the other hand, we can take the minimal Levy in the quasi-split inner form of G and do the same to it. That's another Galois representation of the same degree. The difference is a virtual Galois representation. I fix an auxiliary additive character, and I compute the root number. And then I have a sum over just the same Weil group that it was before. And in here, I have something that I'll define for you in a moment. And then finally, I get the character here. Now, what is this? This is an absolute version of a construction that appears in the paper of Langens and Schellstadt on transfer factors. And it has the following. It has the following explicit structure. You're taking the product over all symmetric roots up to the Galois group. Chi alpha, for each symmetric root, chi alpha is going to be a character on the multiplicative group of the field of definition, which extends the local class field theory character kappa alpha, which is defined on the smaller field. And A alpha is a certain element of alpha cross. And what I'm skipping in this talk for the purposes of time is that you can compute these by explicit simple formulas out of theta. So theta itself, you can write down formulas that specify such things for you. And then you just write down this formula, alpha gamma -1 over A alpha, chi alpha. You put that in, you have this character formula. So now you may think, okay, what's the point, right? I mean, this formula doesn't look any more compelling than this formula. But the point is that this formula was defined in terms of this set, which is specific to p-adic groups. All the ingredients in this formula are valid for any group defined over a local field. And they have canonical interpretations over the real numbers, each of those. And when you put the canonical interpretations over the real numbers, lo and behold, you get the Harishchandra character formula for elements in the torus S of the real discrete series representation that is parameterized by this character theta and the torus S. So there is this formula that gives you the character in the real and in the p-adic case. It's the same formula. So you could think of this as an example of Harishchandra's Lefschetz principle, that somehow real and p-adic groups should have behavior that is in some sense common. The analogy, of course, is not perfect because these groups have other tori and the characters will behave very different on other tori. But on these particular birth tori for the representations, they have the same formula. And once you realize that, you remember how Langlands constructed the L packets, the local Langlands correspondence for discrete series. You take the parameter, you extract from it a character of a torus, and you use it to specify the Harishchandra character of the constituent. So let's do that. Here is how it works. You take a parameter which has three conditions. It is discrete. The image of wild inertia lies in a torus. And the centralizer of the image of inertia is abelian. This is slightly stronger than what I actually do, but the thing that I actually do is longer to state. And this captures almost all, so it's good for the purposes of a talk. Then what you can show is that up to equivalence, phi actually lands in the normalizer of a maximal torus in G hat. So by the standard procedure, it gives rise to a twisted Galois structure on this T hat. And you take its, so this is the twisted Galois structure. And you take S to be the dual torus. And now here comes a funny thing. Chi alphas of this kind are made to order by the theory of Langlands and Schellstadt to provide you with an embedding. So choose any chi alpha, collection of such characters over there. Then the theorem of Langlands and Schellstadt gives you an embedding of the L group of S into the L group of G. It depends on this chi. And now it's cooked up in such a way that your parameter is going to factor through that embedding. And it's going to lead to a character theta chi that also depends on this chosen chi data. All right? But now what you do is you write down exactly this formula here, where instead of the chi data computed, as in the previous case, you just take the one that you have chosen. And you put in the theta chi here that it gives rise to. And then you check very quickly that this formula does not depend on the choice of chi. It just depends on the parameter. Of course, to write it down, you need to be able to put into this character elements of your group. So that means you have to be able to put this torus into your group. This torus itself is not part of the group. So for every Langlands parameter of this kind and every embedding of your torus into the group, you can write down this formula. By our previous work, this specifies a regular supercuspidal representations. And you say the L packet is going to consist of all the regular supercuspidal representations that you obtain for varying the embedding of S into G and writing down this character formula and having it pick out for you the character. And then you can check the following properties of these L packets, that as expected, they are parameterized by the centralizer of phi in the dual group. And if now we're coming back to this problem that this formula, character formula, only held under the compactness assumption, we removed it for shallow elements, but if you actually want to prove something for these representations, you need it for all elements. there are cases in which the formula holds for all elements, and under this assumption you can prove that each L packet has a unique generic constituent. You can prove that the L packets form stable characters, and you can prove that endoscopic transfer holds. So, and I'm currently nagging on Spice and DeBacker to extend their formula to remove this assumption, in which case hopefully we'll be able to prove these same results just in general.
So you have a complete theory of endoscopy.
For these regular supercuspidal representations. So we're still avoiding things where pi minus 1 could be unipotent representations. That would be something to be discussed at a later stage. Yes. Yeah, I think I'll stop here.